Hi everyone, welcome to the third session, which is about the end-to-end downlink data flow. Particularly, we're focusing about the RAN protocols. And if you remember, in the previous two sessions, we covered in details, in very deep details, about the RLC protocol and PDCP, and also we covered the part of the MAC and like how these kind of layers are interact with each other, and what is the impact in upper or lower layers, and so on. So today session we're going to focus on the TCP part. Yes, the TCP, which is a transport layer, it's out of the RAN protocol, but still it is very important to understand, at least from high level perspective, how the TCP operate. Because at the very end, whenever you take any action from the RAN perspective, you need to understand the impact on the end-to-end chains. That's why you need to understand how the TCP layer behave and what kind of impact we are expecting after we tune any parameters, particularly in the PDCP. So in today's review, this is like we're going to cover what's mentioned here. First, we'll go through some high-level introduction about the TCP, and you might be familiar about all of that. This will be discussing in details in the next slide. Then we're covering some of the TCP fundamentals, for example, what means by handshake, what's the TCP header, and again, I would like to stress into this point that the header is very important whenever you study any of these kind of topics, because if you understand the header very well, it will be very easy to analyze any Wireshark logs. It will be very easy in general to understand what's happening in the network and how the layers are interacting with each other. Then we'll go through some transmission TCP transmission types, and this is the most important here because at the very end, whenever you take any action the RAN, this might be reflected in the retransmission zone. And so we need to understand how the TCP interact with the retransmission or what kind of transmission. The TCP flow control and window management, which is point number 4 here. This is like we'll be covering in high level. I don't have a dedicated slide for that, but this is will be kind of covered in high level whenever we discuss the other topics. Then we'll be ending by the what kind of impact we're expecting from the BDCP to the upper layer, which is the TCP. Whenever, for example, why BTCP, for example, receiver ensures in sequence delivery to upper layer, which is the TCP. We'll understand that. And also between the lines, you will understand whenever you tune, for example, the discard timers, what's kind of expected impact to the TCP in terms of retransmission and other things as well. So now let's move forward to see what we have today to try to cover all these points. This is just a very quick recap. I have already covered that part in the session one. I covered in details, but I would like you, if you didn't watch the previous two sessions, to go back and watch this particular area because at the end we are discussing now the TCP part from even sender or receiver or client to the server and so on, and we'll give like kind of a real example from Wireshark today about the HTTP, but it will be mainly covering the TCP part and the HTTP. So again, it's very important to go through again this part if you didn't attend the first session. So refer to the link and the video description for the playlist so you can find the video. So let's move to the whatever we have today. So I believe you might already be familiar about that part. This is like we're giving a high-level introduction, particularly about the transport layer, which is the TCP and UDP. So as you can see from the bottom figure here, and this is also discussed in the previous slide as well in the session one, but let me give a very high introduction. For example, you know this OSI model layers. We have different layers starting from application layer till we reach into the physical layer. Okay, so the application layer, which is usually in the very top part in the layers, this is usually like what it means by application layer. For example, if you're going to do a download, let's say FTP, file transfer protocol, or HTTP, you are going to do a browsing or whatever, Facebook, Udemy, or whatever website you are going to check. So this is like kind of HTTP protocol. So this is your application. This is what kind of application you would like to access or whatever. So the application requires something called process-to-process delivery, which is would be done through the transport layer. And as you can see, the transport layer is essential for in general for enabling the communication between the two application layer, as mentioned here, running on different devices across networks. So, for example, you have uh, one device and you have the application, for example, here, let's say Facebook or whatever, and you have your device, let's say your laptop or whatever, trying to access this kind of application. So the transport layer will be running, will be like making this process to process delivery. And at the very end, we have two types of transport layer. Actually, it's multiple types, but we are focusing more on TCP and UDP, and particularly our session will be about the TCP. TCP refers to Transmission Control Protocol, and UDP refers to User Data Ground Protocol. And this is the globally standardized protocols as mentioned here. And as we have mentioned before, the transport layer it ensures, as mentioned here, reliable process-to-process delivery. Means it doesn't it's very sensitive, or it doesn't require a single byte to be lost. Yeah, for example, this is it's called a TCP connection oriented. It's a reliable protocol. So, for example, if a uh, single byte or one byte doesn't make it to the other side, let's assume that you have 1,000 byte transferred from X application X to Y. So if one byte, single byte, being lost or whatever, the TCP has a mechanism to do the retransmission and to transmit that data, and it will send another copy from this data. So this is the main idea. It's very reliable process. It requires 100% to make all that data to be transferred to the other side. This is the differences between UDP and TCP, because TCP at the end works at something called send and forget. It doesn't have any retransmit protocol, so it just send the data. If it's lost, it's lost. And what's the differences? Because, for example, the TCP, as you can mention here, this is required, it's connection oriented, as we mentioned, and this is recover all the lost packets. And this is usually called byte stream, because this is track each and every single byte. That's why it's called byte stream, and we'll go through this in the next as well. And this is for example, requiring for the software packages, like for example, HTTP and FTP. For example, you cannot access the web if you have a missing packet, so pictures or whatever will not be found. So that's why I needed to have this kind of TCP to ensure that you are receiving all the bytes, all the data to be able to access the, for example, website. And even if you're downloading a file and there's a packet loss, this means your file at the very end will not be working. That's why it's required to have this kind of reliable connection, which is a part of TCP functions. And for the UDP, just more about the latency. It needs something to have fast and simpler, and it's more about the latency. That's why it's using for this kind of application, like the audio or video streaming, for example, voice over NR or VoLTE or whatever, which require much higher latency, and it's not very sensitive to the packet loss compared to the other, which we just mentioned here, data service as HTTP and FTP. Just a very high level for those. So now let's go to the details for the next slides. So actually, this is the main properties of the TCP, and this is very important to understand it. As we highlighted, the first part, if you look in the top left here, is called TCP is a connection oriented. What it means that connection oriented, means the application or the client to the server, the side, for example, the sender and the receiver, they need to have a connection between each other to communicate some information. And this is very information that you need to communicate some of the parameters, and these parameters will facilitate the communication. Okay, and this is usually done through something called three-way handshake. I will explain this one with a real example. But for example, this is how we can see there is a connection request from the sender to the receiver, then connection acknowledgement and connection established. During that, they are transferring multiple information. We'll go through all of them in details with a real example. For example, here it's telling them that the port number I would like to access is 80, my IP address is XYZ, and I can, for example, send this. This is, for example, here, this is the information of the sender. The sender is sending this information here. So the receiver receives the information from the sender, telling him my port number is 200, IP address XYY, and the sender, I can send up to 1,500 bytes per second, for example. And then the receiver will be replying with connection acknowledgement, telling him similar information, what is being confirmed, then the connection is established, then we can start processing the data. And both of them, for example, now have some important parameters, which like these parameters, as you mentioned, refer to how efficiently the sender and receiver can process incoming data from each other. I'll explain that part, but it's simply, for example, the most important. This is for sure the port and the IP address for both sender and receiver. This is usually called it 4 tuples, but anyway, this is like communicating the what is my port, what is my which kind of port I would like to access, what is the IP address, and so on, and also it's like exchanging something called, for example, the window size. Like for example, the sender telling the receiver, this is my window size. If you would like to send this kind of data, you can send it to me at this particular rate, and this is the maximum I can handle, and the same from the receiver to sender. And by the way, in general, the TCP is a duplex. It's bidirectional. For example, the sender can be sender and receiver, and the receiver also can be receiver and sender. It can send and receive data at the same time. And also, there's something called a stateful protocol and a byte-oriented protocol. This is just summarized in one word, which is called data housekeeping. That, for example, the TCP sender and receiver keep always tracking the data sent and received. For example, here it's saying I have 100 bytes sent. I have 300 bytes is going to be sent next, and I already received 100 bytes. Okay, and for example, this particular item need to be resent or retransmitted or whatever. So this is what it means by stateful protocol means, because it's kind of data housekeeping. It's having a buffer to give the state of the packets, how many packets being sent, received, what is the next, and so on. And byte oriented again, as we mentioned before, because TCP track each and every single byte. It's not about packets, it's about it's byte. So it's TCP keeps the track of data at byte level, not at a packet level. Okay, this is very important as well. This will be explained during something called sequence number and also the segment, TCP segment and so on. This will be explained in detail. And also we have this is one of the most important as well. It's guarantee in sequence delivery. For example, it can handle out of order delivery of the packets. For example, assume the example in the bottom right here. You have the sender sending packet 1, then packet 2, then somehow during the journey from the sender to the receiver, somehow the receiver received the packet as in the wrong order, which is sequence number 1 and 2. And at the TCP level, it will guarantee that those packets, even they are received in the wrong order, they will ensure that these packets are transferred in the correct order to the application layer. So that's why it's called out of order delivery of the packet. So at the end, even if the packets received in wrong order, it will make the ensure the data is delivered again, like reordering the data and sending in a correct order, as mentioned here. And the very end here, we just mentioned also in the previous slide, reliable delivery, that ensures there is no a single or single byte being missed, or none of the packets has been missed by implementing something called automatic repeat request. We also highlighted that before. This is the transmission mechanism. And in general, this is the most important feature in the TCP, and there is multiple types of retransmission we're going to cover in the next slide. So now let's move to the next part, which is we'll be talking about the TCP header and the handshake, how the parameters is being communicated in the very beginning, and how these parameters can be used, and which one we need to focus on it. And then we'll explain one by one what is the impact between the RAM protocols up to the TCP layer and so on. So let's move to the next slide. Okay, this is just a very quick high level. I will not cover it in details here. I'll cover it in this next slide, but just as on a high level, this is meaning by for example, the three-way handshake. For example, the client and the application server, the client will be sending synchronization message, sync. I would like to sync with you. And this sync message will cover multiple parameters. And these parameters also having kind of included as a headers, but these parameters will be added here, and the headers will be added within the sync to the application server. So that the client or the sender, whatever the name, is telling him, this is my parameters. You need to keep or consider whatever header and parameters I'm sending to you, and this is my capability. Then the application server will reply back, yes, I received your message, sync acknowledgement, synchronization acknowledgement. I feedback to you that I have received your message, and also this is my parameters. To tell him this is my parameters, which you need to consider whenever you're going to send data in the future. Then the client again will reply with the last part, confirming now we are in sync. Now we have the three-way handshake. Now I can start, and we can start sending and receiving data from each other. This is like the high-level view. We have, for example, TCP, you have the IP header, it's there. We have the source and destination ports, and we have the sequence number, acknowledgement number, header length, and something called flags. All of that will be covering details, and window size. For example, sender would be sending to the receiver, telling him, this is my window size. So you cannot send data, or client to application, telling him this is my window size. You cannot send any data, for example, greater than this window size or whatever. And there is just checksum, this for error correction, and so on. So let's move to the next one. Then I will open our Shark example to show you each one of these messages, what it contains, and what kind, as a high level, these why we need this information from Wireshark, and what kind of use cases we can use it in our analysis and so on. So let's move to the next slide. Okay, here you can see I just give in the right side here a table with all the information within the handshake. Okay, for example, this is within one of the messages telling all the information which we have here. So in this case, for example, you can take and use this information. Like in the right, you can quote it or take a picture. But anyway, I will explain this one by one through the Wireshark itself. And in the top left here, this is the example I'm going to explain now. For example, here I'm going to open the first three messages, which is the send, then send ACK, then ACK, and I will tell you what we have. And again, this is HTTP example. For example, HTTP over TCP. HTTP is the application, so it will be over the TCP, which is a transport layer. And this is, as I mentioned before, whenever you would like to open a website, should be happening first. You should have the three-way handshake until you have it's completed. Then the client can send HTTP get command, like trying to access. Then you will have a response from the application to the receiver and so on. So let's move to I will open the Wireshark, show the examples, and try to explain in high level what it means by each of those headers and messages here. And also afterwards, I will explain with kind of some slides visualization about some of the headers which we are going to use all over the slides. So let's move forward to see what we have. Okay, as you can see here, this is a TCP handshake example. So, for example, here I filtered on the whatever we need as an information. For example, here I click in the first message. But if you look as a high-level view, you have the source and destination. The source is your client, assuming coming from the mobile and trying to access to HTTP application server. So in the application server, so I just need to do this three-way handshake to again exchange some of the parameters to be able to establish a connection, because at the end TCP called connection oriented, you need to know each other, you need to communicate the parameters in order to be able to know what they would do next about the data transfer. So initially see the first one, which is called, for example, if you go to here, source destination, they have the protocol is TCP, and they added some columns here, TCP length is 0. I will explain all of that. Then we have here some information. For example, if you look here, you know that HTTP using port 80, so it's 80, synchronization, sync message, sequence number 0, window size, length, MSS. So let's go through the header and the parameters in general of TCP to explain one by one. So for example, here this is what you will see. You have the frame, Ethernet, and Ethernet transport when you click in this message. Okay, so I'm going to open the transport transmission control protocol, which is the TCP. So initially you'll find there is something called this is source port. This is telling him this is my port. The client telling him this is my port, and I'm trying to access, for example, the HTTP, which is port 80. This is for the client. As you can see, this is for the client. This is just a very important stream index. Will be a unique stream index. For example, let's assume you did HTTP for one website. Let's assume Google, and now you are trying to access another website, Facebook. Okay. In this case, you have two TCP connection, different TCP handshake, because you are accessing different applications. So you'll have stream one, stream two. So whenever you do an analysis, you can focus on a particular stream. Okay. Each of the TCP have a different unique connection. So it's identified by this kind of stream index here, stream index one. And here just telling him, for example, this complete conversation, just telling him conversation completeness, saying this is incomplete, because usually if it's complete, for example, you should see, for example, here one as finished. Here there is a reset if the connection be resetted, or the connection terminated or finished, you finish by yourself, so it should be one. So it's just selling incomplete because of that. But here there is sync message confirming being sent, sync ACK be received, and the last ACK being received as well. That's why it's saying the connection having this kind of message, data transfer, sync, but this is not really important. Then here, the TCP segment length, this is telling you what is the length of the data. So Usually, this kind of handshake, it's having almost, you can say, ghost byte, which is almost zero. It's 1 byte or whatever. Yes, it's having the header of the IP and the header of the TCP itself, but the data itself, the payload is zero. There is no payload. It's just about the headers. Okay, so you have the TCP headers, which we're going to explain, and you have the IP header, and depend on your IP version 4, version 6. For example, version 4 can go up to 40 byte, version 6 can go up to 60 byte. And you can see down here you have the sequence number. Okay, this is like usually the sequence number, as you can see, this should be the number row. It's like very big number, okay? But this sequence number, usually each byte will have a sequence number. I'll explain this one with version example also next slide. But let's just try to get an understanding frame. For example, I'm starting first with sequence 0, and now I have almost zero bytes. So I'm expecting that only 1 byte will be sent. So I'm expecting the next one will be 1. Let's assume you have the length of the data here was 100 byte. This means the expected will have sequence number from 0 to 99, and the expecting sequence number will be 100. So I will be waiting for example, the receiver will be sending acknowledgement number. I'll explain this one, 100, for example. If you look into here, this is first sequence number is 0. Acknowledgement, this is the client is saying that I have acknowledged 0 because you didn't send anything for me yet to acknowledge. But if you go to the other side, we'll explain that, for example, in the other side from application to client, he replied to sequence number 0. This is my sequence number starting from 0. And I acknowledge that I received already sequence number 0, and I'm waiting now for sequence number 1. This is like accumulating, telling him I'm waiting for the next sequence number. But again, the sequence number here, this is assigned by the sender. Okay, sender can be either way because at the end it's a duplex mode, TCP as we highlighted, so both of them can assign a sequence number, and the sequence number tracks each and every single byte. Again, keep this point in your mind because we'll explain more details. But again, sequence number is tracking each and every single byte. So again, if it's starting from 0 and the length was 100 byte, so the sequence will be from 0 to 99 because this is 100 byte, and then each one of the one sequence is equivalent to 1 byte. This is like added the relative sequence number that's added from Wireshark to make it more easy, because at the end it's very difficult to track this kind of numbers, as you can see in sequence number row. Then the next sequence number I'm going to send is number 1. So this is also relative. This is telling the receiver about this kind of information. Acknowledgement, I didn't yet receive any data to acknowledge, so the acknowledgement is 0. And this is the length of the header. For example, the header length is 40 bytes of the TCP. Then you have the flags. Inside the flags, you find here, for example, it's just telling you this is what kind of connection you have. What you need to know for now is just the sync. Okay, sync means this is, if you look in top right here, this synchronization. This is 1 means this is sync set. This is I'm sending a sync message. Then you have the window size. The transmitter, which is the client, let's assume it's the mobile device, is sending to the receiver, which is the application server, telling him this is the maximum size I can receive of data. This is my maximum window size. So it's this number is 54,240. This is like in byte. So this is the maximum window size of the sender where it can, so from the client where it can receive data from the destination, which is the application server. So it's just it's calling window advertisement. Each of both the sites will advertise their window, telling them their capability about the data which can be sent or received, and here telling them about how much it is going to receive. Then going checksum. This is just for the check if any errors and so on. But the important one here, it's the TCP options. Again, you can see the option bytes, 20 bytes. This is the header. Header is up to 20 bytes again. Okay. Header length. This is usually, I think, for the IP. But anyway, options, TCP options is 20 bytes. This is now, as I mentioned, the payload itself is 0, but the option, the TCP option having 20 bytes. It having multiple options here. This is the maximum segment size. This is the maximum size it can transfer. For example, one segment can have 146 bytes. Okay, this is like, for example, if it have packets coming from the application that one would like to transfer, this is the maximum in one shot, in one can be sent from the, for example, client to destination. SAC permitted, this will be discussing in details. This is something called selective acknowledgement. It's telling them I'm supporting the selective acknowledgement. I can support the selective acknowledgement feature And this is one of the most important what I'm going to discuss in details. But keep it for now. This is just telling him, announcing their capability. The sender is, or the client is telling the application server or the server, I'm supporting selective acknowledgement. Then you have the last thing here, which is window scale. This is usually used to multiply this window size just to make kind of, because at the end, the window size having a maximum size here, but this TCP option is allowed to even increase the window size. So you just multiply by 128, you will get your uh, uh, actual window size. This is the main idea about that one. And this is all about the TCP uh, headers. But let me first now go to the next message, which is from the server to the client, telling him what is my capability. It will have almost the same information, but as you can see here, telling him from HTTP, from the application to this port number. This is the port of the receiver, which is being sent in the first beginning here. So again, you'll find the same, almost the same information, announcing the source port, destination port, IP, and also again, if you look into here, this is acknowledgement will be one now because it's saying that I have received your sequence number 0, so I'm waiting for the next one, which is 1. So it's giving acknowledgement about the next data which going to be with. And here now it's telling him my sequence number is 0, and next one I will be waiting for 1. So I'm expecting that at the very end, this one will, the client will reply with acknowledgement 1 as well. Okay, and here if you move forward, it will be exact the same information, but again, TCP option, very important. This is again telling him my maximum segment size, which I can transfer, is 146 uh, bytes. And here you can see that the saying that send packet doesn't contain a SAG permit options. Okay, this doesn't contain a SAG. This just saying that I don't have this kind of options for the selective acknowledgement. Then the last part here is just from the client to the application, just confirming again back, confirming back that okay, I have received. Now we can start communicating the information. So the client, which is the UE, for example, will start sending HTTP command, trying to access a particular website, and even you can get the website information because this is HTTP, right? So this is HTTP get command. So you'll find now it's HTTP over TCP. You can even know the website information from here. For example, here I was trying to access udemy.com. Okay, so this is get command as I mentioned before. So moving forward now, this is acknowledgement and so on. And now the after all the web was being able to be accessed and so on. And within this part, if you look into this is the TCP segment length. It was 324 before it was 0. So this 324 byte. So if you open the again, just quick one here, TCP segment length is 324. So we have uh, this is the length in byte. Then sequence number is 1, starting with sequence number 1. So I'm waiting now to have it's from 1 to 325 because at the end this would be your sequence number covering what 325. So you tell him next sequence number I'm going to send is 325. So if the receiver replied with 325, as you can see here, this is saying now you can send me back the 325 packet. So if you go again for client to the server, you look into the TCP segment is 300, for example. This is from the application to the client. Okay, this was from the client to application. And just again, the application to the client, you will see that here it just acknowledge the packet, telling him I'm waiting for 225. Then again, here it's send it again, telling him I'm waiting for 225, but I have some data also to transfer to you, which is the data length is 704. And if you look into here, it's saying that the CV segment length is 704 and the sequence number is 1. So I'm waiting your acknowledgement to send me 705. As you can see here, it's having a 705 as acknowledgement. This is confirming it's have received the data and waiting for the next one. I'll explain this one in details on next slide. So now let's go back to the slide, see to have, but this was about the three-way handshake, which is very important to understand. So going back, you have all the explanation for whatever you have mentioned here. Okay, this is like in case you would like to read it in details, you can read it and try to again open the Wireshark. You can capture even from your laptop directly. You don't even like required to connect to any network, just laptop through your Wi-Fi. You can try to access and capture the data. Now moving forward, I would like to explain in details more about the sequence number to make it more clear because the example was kind of going very fast. So let's explain about something called segment and sequence number about the headers, which is very important because I'm going to give a lot of examples, and these examples need to have more clarification and more explanation. So as you can see, this is like the slide will be explaining about in more visual example. Also, the other next slides will be covering the same and in more details. TCP segments, we have the TCP header, have something called segment and sequence number. The TCP deals again with it's a byte oriented, but this byte oriented send in term of segment. For example, if it's assuming the bottom left down figure here, assume that you receive the data from the application server. Okay, so the sender or the TCP in general will encapsulate application data, the data coming from here, into segments. Okay, and this segment can be determined have a varying size, and usually the TCP, as I mentioned very earlier in the first session, TCP will take care to ensure that this like as much as possible that this kind of segment size, the maximum data, for example, can be sent within the segment size is not exceeding across a specific, for example, number, let's say 1,000, 2,000 byte or 1,500 or whatever, to try to avoid as much as possible the IP fragmentation. Because if you send a packet greater than the required IP packets, with the IP packet which can handle this kind of data, so the IP layer will like try to fragment this layer into small packets. So you try to avoid this. The TCP is trying to avoid this. But the most important now to understand, the data coming from application will be encapsulated inside a segment. Okay, so in this example, I'm assuming you have multiple data being received, and the maximum segment length is 100 bytes. Okay, so again, we mentioned before that each segment contains n bytes. For example, assume that the segment, we have three segments. One segment contains, each one of those segments contain 100 bytes. Okay, each byte should assign with a unique sequence number. I mentioned before that each byte should have a sequence number. So now assume the sequence number is starting from 600. This is like usually the sequence number is random, set it by the network. Okay, but it will be accumulated. Like whenever you have additional data, the transfer, so it will start counting and increasing sequentially. So, example, assume here you have starting from 400, the first segment, then 500, 600. So the first one is being sent as 400. This is the first sequence number. So as long as, because the byte or the segment length, this is a segment, and having sequence number 400, 400 means that because the segment length is 100 bytes, so this is means from 400 till up to 499, this will be sequence number. Yes, the number you will see is 400, but again, because it will cover the each of the bytes, 100 bytes, should have one sequence number. So the starting point is 400, ending point was 499, which is at the end each sequence number having one byte. So if this one is, for example, is 200, so this one would be ending by 599. If this one, if the segment length is 300 byte, then this one will be ending by, for example, 799, and so on. Same example here, I'm assuming that after this one being sent, the second one being sent, starting from the after 499, starting from 500 up to 499, from 600 up to 699. So again, TCP is byte oriented because it's track each and every single byte, but send this, it's encapsulate the bytes within the segments, and within the segments there is a sequence number. The sequence number for each byte should have a one sequence number. Okay, and this is how the data will flow from application to the lower layer TCP, then from TCP to the IP, then moving to the network, coming back, and till it receive the other end, and so on. So this is more about that part. Now let's jump for the next part, which will be quick about something called TCP segment types. Just a quick and very high level about the segment types, just in case to understand what's the difference between segment type. Again, the segments used to carry the bytes. Okay, so I would like to explain the different types which we have, because this will also be useful whenever you analyze any Wireshark log. So in general, as I highlighted before, TCP communication is duplex, means bidirectional, means that you have the sender or client and server, sender and receiver, client server, both of them can work in the same direction. For example, both of them can send and receive data at the same time. That's why it's double connection. So that's why you have three types of TCP segments. Something called data segments, pure segments, or data and ACK segments. It's I think it's kind of clear from the explanation itself, but let me explain with the example on the right. Data segment means it's purely data, just contain only application data. Okay, so for example here, if you look into this example, this is data set containing sequence number 200, and the segment length is 100 byte, means the TCP segment length is 100 byte, means the sequence number again from 200 to 299 as we explained before, because this is the end 100 byte. Okay, sequence number is from 200 till 299, but it will just state it as 209. So I'm waiting, the next one should be 300 byte. So for example here, the TCP receiver here replied with acknowledgement. Okay, this is acknowledgement 300, telling him I'm waiting for next one, which is starting from 300 as a sequence number. Okay, as you can see here, first one called here data segments. This is the type. It's pure data, only data. Second one here, it's pure acknowledgement with no data. But in case if there is a data with the receiver or the TCP, for example, other side required to send, let's say an application required to send, it can make this kind of data plus acknowledgement. I will show this one shortly. But this is now the two types which you have. The first one is data send. This is pure data segments, and you have the acknowledgement, which is the pure segment. Now, assume there is a new data which being sent afterwards, which is starting from 300, because already the receiver received till up to 299 sequence number, which is at the end 100 byte. Then it sends the sequence number 300 with 100 byte, also size, TCP segment length. So now the receiver has some data to send as well. So this time it will tell him acknowledgement number 400. I'm waiting for the next one, which is starting from 400, sequence number for 400, but I have a data to send. The sequence number of this data is 1000 byte. Sorry, the 1000 sequence number, but the data size TCP segment length is 100 byte. So this means I'm expecting that this one should reply again with a sequence number. This is sending the new data, and it also should reply with acknowledgement with this sequence number 100, 1150, because at the end add this together, so it will be, this is the next telling him I'm waiting for that one. So we have three types of data: data only, you have acknowledgement only, which is called pure segments, and you have data plus acknowledged segments. At the end, this is whenever the one of the sides having data to send and also need to acknowledge some of the data. Okay, so this is just a quick information here. Let's move forward. Now moving to the most important part we have in the TCP, it's about the TCP retransmission in general. And TCP, again, we mentioned it's reliable delivery, right? Which is ensures there is no a single byte being missed, not a single byte of data being missed. That's why it needs this kind of retransmission mechanism. And it's based, again, on automatic repeat request. But in TCP, there is two mechanisms of retransmission. So something called, as you mentioned here, retransmission timeout or standard retransmission. This is just simply based on timer. For example, if you look into the top figure here, the sender sent a packet here, and it was waiting for a reply. But somehow the acknowledgement of this packet, which is again sequence number 100, length 100, so we're waiting from 100 to 199, for example. Here it was waiting acknowledgement 200 for the telling him I have received your data, send the new one, but somehow it's being lost. So there is a timer started here. Once for each segment going to be sent, there is a timer will start. This timer, it's called RTO, retransmission timeout, as you mentioned here. So this timer, if expired before receiving the packet, it would directly retransmit. Okay, so now it's transmitted again, as you can see, sequence number 100 is being retransmitted again. Once acknowledgement, the timer will be reset and restarted. It will just stop, and it will just start whenever a new one is being sent. So the first one is timer based on a timer, and I will explain this one in more detail in the next slide. Timer based mainly. This is the first type. The second type is a fast retransmission, and this is actually having under that have two categories or two types. Fast retransmission can be based on something called duplicate acknowledgement or selective acknowledgement. I will explain this part in more details next slide as well. But again, this is a quick example. What it happens, for example, assume this is not based on timer. This is just based on feedback from the receiver. For example, sender is sending for segments, as you can see here. Segment number one was sequence number 200. Segment number two is sequence number 300, 400, 500. So 4 segments, each one having a different sequence number. So at the TCP itself, it's received from 200, which is again, I assume the TCP segment length 100. So this is sequence number. This is the receiver buffer. It received data from 200 to 299 byte. So and 300 to 399 byte, which is starting sequence number 300, for example, it's being lost. The next one here is being received, which is this one and this one. So now the receiver having a buffer, having a gaps, having holes. There is one packet being, or sorry, one segment being lost in between, as you can see. So it cannot forward this data to the upper layer, which is the application, until it having a sequence. So it must recover the lost packets first. So this is not based on timer. Once it's received data out of order or completely missed or lost, it will send something called duplicate acknowledgement. We'll explain in details. Sending him, okay, it will not tell him I need the next data. The expectation in normal case scenario that if all that received, it will tell him acknowledgement 600. I'm waiting for the next one. But now it will tell him I'm waiting for 300. But duplicate acknowledgement, it will send it multiple times. Selective acknowledgement will send specifically for a specific packet. I'll explain this in the slide. But just simply, this is not based on timer. Just fast retransmission based on feedback base. Whenever there is out of sequence delivery or a missing packets and there is a holes in the receiver buffer, it will directly send asking for the same data was being lost. It will ignore the new one. It will just keep it in the buffer until it's recovered the missing one. So it will be able to transfer the data in sequence to the application there. So now let's move forward to check in details these two types, because this is the most important. Then we'll be ending by the example of the PDCP impact versus the TCP. So the first time I would like to explain, because it's having some important concept and you need to understand it, because somehow you can think about it whenever you tune, for example, the SCAR timer from the PDCP time side. For example, here this is a sender and receiver again, and this is example for retransmission timeout. So for example, assume that initially here there is a sequence number being sent, and initially the RTO transmission timeout, this is like kind of there's initial value. This is based on the TCP implementation. Usually this value as an initial for most of the TCP will start with 1 second. Okay, it can be higher, can be less, but usually it's 1 second. So I'm assuming in this example is 2 seconds. So this means that the initial for the first transmitted packet, okay, of the, for each segment transmitted, it will have this initial timer. So each segment transmitted will have its own timer. Okay, so the same packet is being transmitted sequence number 100. So the initial RTO started with, for example, with 200 with 2 seconds. Okay, the first one started with 2 seconds. So this should give initial RTO value. So it will wait for those 2 seconds. If there is no acknowledgement received within the 2 seconds, that will make the retransmission. So this is initially, as mentioned here, there's an initial RTO. When a TCP connection initially is established, the initial RTO value is set by the implementation. Implementation, for example, in the device, the Windows, I will show some examples in the next slide as well. Your Windows can have its own initial RTO, and also the devices, the application server, whatever, all of that. So, and this is in the initial RTO acts as the starting point, because yet there is nothing called round trip time samples. I will explain that part, because this is only the initial value. At the very end, the RTO should be dynamic to the network latency, not like to keep it very large or very small. I will explain why as well, but just the initial value. Now what will happen? Assume now, if you look into here, I'm assume before anything, I assume there is multiple sequence number being sent. Sorry, sequence number or segments. I assume here, for example, 5, but let's assume 20 or 30 or whatever. But I assume there is multiple segments being sent, and all of them was being acknowledgement. Based on this multiple segments, for example, let's say 20 or 30 or 50 being sent an acknowledgement, usually 20, for example. Now the sender will start calculating the RTO based on the round trip time. For example, if the round trip time from, let's assume you have 20 segments as a historical data being sent and acknowledged. So the round trip time is the time from the sender to receiver for that packet, and back from the acknowledgement from the receiver to the sender. So this is the round trip time. So for example, it will take the weighted average for all the previous there's a formula for that, but no need to go for the details. But it will take the weighted average for all the previous transmitted segments. Then it will calculate the RTO timer to match to the network round trip time. So I assume for all these packets, the round trip time was 1 second. Okay, but Ask yourself why it's doing that. Because at the very end, for transmission, if the timer is set for a very large time, let's assume 5 seconds, 8 seconds, 10 seconds, and there was a missing packet, so the TCP sender will wait idle mode for a very long time until it sends the retransmission, right? If the packets was not being sent for a very long time. So this is not good for the network at the end because it will increase the delay, it will underutilize the network. Assume the opposite way around. The timer is very short. Let's assume 100 milliseconds. So it might send the retransmission, even the acknowledgement was going to be sent. And if this is might increase the network congestion and also unnecessary retransmission. That's why it needs to be computed by the network to try to match with the round trip time of the signal transfer for the TCP sender and receiver. That's why it's taking the historical initial start with initial value, then it take the historical data for the round trip time from the previous signals. For example, round trip time again from sender to receiver as a send, first one, then the back to the receiver to the sender. So it calculated this one, find it 1 second. So again, it will be waiting for 1 second. If acknowledgement is fine, then the next part there's something additional like points also we need to be like considered whenever you have a transmission amount. Assume now your computed RTO is 1 second. Assume you send this packet and the timer is started, and when the timer started, you didn't receive within the 1 second the acknowledgement. So in this case, the RTO expired, so there will be a retransmission for the first packet. So what will do the transmission sender now? There is a mechanism called exponential backoff. In this case, it will increase your RTO by double. For example, your RTO is 1 second, it will increase to 2 seconds. Why? Because simply it's just to secure there is no like to giving more a chance to the receiver to send the packet back without sending again this transmission again and again and again. So just like guaranteeing that there will be no more transmission. Also, this is to avoid network congestion, for example. So now assume there is again it will not be received. So again to double your RTO, the sender will based on this exponential backoff from 2 to 4 seconds. Now assume now this packet is being recovered, okay, and now the connection will continue. So now what will happen? It will not reset this one to 1 second or 2 seconds until it's having a direct response. For example, assume here there is a new packet being sent with sequence number 700 and it directly being acknowledged. You will find that your start point, even the packet was being acknowledged here, the start point was 4 seconds. Again, which is the last one for the exponential backup. It didn't reset this one to the RTO value because it just need to ensure at least the next one, the next retransmission after the first recovery, it's just being success transmission segment is just in the first attempt it's being recovered. First attempt means there is an indication of a network recovery, so there's no problem in the network anymore, so it can reset back the timer to the calculated or computed previous computed RTO, which is 1 second, and now it can start working and so on. So this is just in general. So what is the takeaway from here? The takeaway from here that, for example, assume you have a PDCP score timer, and this PDCP score is set for a very short time, and the data, for example, let's assume is set for 150 milliseconds, and the data set in the PDCP buffer for 500 milliseconds, 300 milliseconds, then it's being discarded, and this one is already 1 second, or let's say over 500 milliseconds as a network. Okay, this means that PDCP is even discarding the packet very early. So okay, so this will lead to unnecessary transmission from the TCP. Okay, so in this case, you need to try, for example, to make it, let's say, if it's 500, make it 500, or to increase it a little bit, just to ensure that the TCP is not discarding before the TCP do the retransmission. Because at the end, if the PDCP is able to send within the before the retransmission time of the sender or the TCP, in this case, this means you will guarantee that there is a rest retransmission from the TCP perspective. This is the main takeaway from here for this time. Now let's move to the next type to explain it as well, because this is have kind of a relation with the parameter and the BTC, which is called out of order delivery, which I will explain in the very end. Before going further, I just would like you to do this example. There is, as you can see in the figure in the right here, this is from my laptop. I just write the bottom command here in the PowerShell, get in net TCP settings. I would like to check what is my laptop settings. You'll find this initial RTO value, which is a retransmission timeout, is 1 second, as I mentioned before. It can be higher, can be less, or whatever, but usually it's 1 second as a common for most of the TCP implementation. And there is also something called minimum RTO. Minimum RTO meaning that even after computing or calculating the TCP sender is calculating the new RTO based on the historical round trip time of the historical segments being sent and received, it cannot go below this 300 milliseconds. This means this is the minimum RTO. So even if it's calculated as 200 milliseconds, it will keep it at 300 milliseconds. This is also, as mentioned here, just prevent RTO from being set too low, which could cause premature retransmission and error congestion. Same for the initial RTO. This is just a starting point for the retransmission time, which later on will adjust dynamically again based on the network round trip time, as we highlighted in the previous one. Just, you can try it and check what you have in your laptop, for example. Now in the next two examples, but maybe before going to this one, let me show you a real example of the, before explaining this duplicate ACK, a real example of the retransmission based on RTO, based on Wireshark. For example, here I'm showing a quick one here. For example, this is during the TCP handshake. The client sent the send message to the server. Then here it started, for example, at 00. Then 3 seconds later on, again the client sent a retransmission because within 3 seconds it didn't receive the timer. 3 seconds means here the initial RTO was set to 3 seconds for this particular TCP implementation. Okay, so you'll find that transmission happens directly after 3 seconds, 3 point something, because the timer is being expired, so it must retransmit. Then directly it was being acknowledgement by the receiver here. This is example for the RTO timer, which is again can differ from one network to another. So example, assume that you will have multiple streams going on in the PDCP, and the PDCP discarded the data very early, for example, at 1 second or 200 milliseconds. So in this case, it will never receive it will never being reach to the TCP application server, right? The application server, so it will not be able to reply with acknowledgement. So in this case, the TCP will need to retransmit based on this time. Just a quick example here. Now let's go back to the new or the other TCP transmission types. I already give for this type, it's called duplicate acknowledgement. I give a quick overview in the beginning, but let now show you an example, okay? Assuming the right figure here, we have the sender again and the receiver. Assume you have the receiver sender first sent this segment with sequence number 200 to the receiver, and it was being received correctly. Then it sent the second segment with sequence number 300, but it was lost. Then it sent a third one with third segment with sequence number 400, correctly received, also 500 being received. So this is how the buffer of the receiver will look like. They receive the bytes from 200 to 199, and 400 to 499, 500 to 599, as an example. And the one in between here, which is from 300 to 300, was being lost. So now there is a hole in the TCP receiver, okay? And there is, again, the receiver cannot act with that, cannot transfer it to the application layer until ensure that, first of all the data being recovered, and also to transfer the data to the application in sequence delivery, as we highlighted before. So in this case, the TCP receiver should act. This is not based on timer. This is fast retransmission. Once it's discovered there is a hole and gaps in its receiver, it will need to recover this data quickly without waiting for any time. So it will send something called duplicate ACK. In this case, it needs to send multiple ACK, the ACK for this message, 300, telling the sender, acknowledgement, I'm waiting for 300 because I didn't receive it. So I'm waiting for this one. I received till only 200, 299, but the receiver will understand that he need to, the sender will understand he need to retransmit this 300, but he will not directly retransmit until it receives, for example, here you can see, first receive at 300, then the sender can still continue sending more data. As you can see, it's sending 600, 700, 800, 3 segments with different sequence number. Then how this is the buffer looks like, but still there is a missing here. See, till now the sender didn't send a retransmission. Why? Because it needs duplicate ACK based on a threshold. For example, there is something called the duplicate threshold. For example, it's at unit 3, and this is the standard for the network. Means that it needs to receive 3 acknowledgement of the 300 to be able to send the retransmission. So again, the TCP receiver send 300, okay, 300 again, second one, then it send the third one here. So you'll see that even it sent the fourth one because this one was not being transmitted, but once the sender received the number 3, the acknowledgement, duplicate acknowledgement number 3, it will retransmit the sequence number 300. So now this is how the buffer being recovered. So now the buffer is fine for the receiver. So that has been, so this is called duplicate acknowledgement. I will explain this one, what is the relation with the RAM protocol, but you can see after the recovery, now the TCP receiver will not send any more acknowledge 300. Now it will send the new expectation. This is my buffer. So I'm waiting for the here from the gray one. I'm waiting for the acknowledgement 900. This is the new packet segment. Sorry, we are dealing again. Take care that it's called segment in the TCP. It's called packet in the IP. Okay, so we're waiting now for the new segment, which is we're starting with sequence number 900. Okay, so first of all, there is two things I would like you to understand. There is a duplicate threshold. This is based on the implementation as well. And also, I highlighted in the TCP retransmission before in the RTO, there is a maximum number of transmission retry. For example, the network cannot retransmit the packet forever. So it should have a number. For example, also based on the implementation, and usually this one is 3. Okay, but actually there is one limitation here of uh, of this mechanism. Okay, if there is a multiple holes, for example, assume there is one hole here, and also assume this one being lost, second one in here, and also 3 holes or whatever, it cannot recover all holes through one message. It needs to send, for example, 3 duplicate acknowledgement for the first one, and this one is also lost. It will send again 3 duplicate acknowledgement, and so on. If the third one is being lost, I'm making 3 holes in the buffer. So this is require multiple duplicate acknowledgement, and this is not good for the network, right? Because at the end, sending consecutive number of for each and every single hole, this is also can increase the congestion in the network, and this is not good for the network utilization. And also, it's not very fast because at the end we need something to try to recover all the holes as much as fast as possible. That's why we have the second type, which is called selective acknowledgement. Now we discussed about the duplicate acknowledgement. We have the selective acknowledgement, which can actually repair all the holes at one shot, at one go, which as I will explain in next slide. So the next one here, it's about the second type, which is the selective acknowledgement, which is overcome the drawbacks of the duplicate acknowledgement. Yes, duplicate acknowledgement for sure it's very fast as well compared to the RTO, but still it's having some limitation as we highlighted before. If you remember in the very beginning, I show you in the TCP header something called SAC, SACK, selective acknowledgement. This capability at the end maybe the implementation TCP implementation will not be supporting the selective acknowledgement. So at the end, he will just follow the duplicate acknowledgement. So this is again depend in TCP header. That's why it's very important for the analysis during the handshake to check the capabilities being exchanged between the client and server to know what kind of capability they have. So for example, I show you that for example, client will support selective acknowledgement. This means he can do this kind of selective acknowledgement. But let's understand first what means by selective acknowledgement. So in acknowledgement, like let's go with an example. It's showing you, for example, again, 4 segments being transferred, starting sequence number 200, 300, 400, 500. This one is being lost. Then again, another 3 segments being transferred, 600, 700, 800, and yeah, actually this should be the opposite way around, but anyway, this one should be 600, 700, and 800. So now, what will be the buffer looks like? Buffer supposed to have 6 segments, each one having a number of bytes and a sequence number. For example, here it received 200, received 400, and it lost 300, and received 500 and it lost 600, received 700 and 800. So now you have 2 holes. Okay. So in the duplicate acknowledgement, you need first to send 3 duplicate acknowledgement that one. Then afterwards, you send additional 3 duplicate acknowledgement. Solve this one because as you mentioned, duplicate acknowledgement, the limitation that it cannot recover the different multiple holes at the same time. Okay, so in this case, there is something called selective acknowledgement. As you see, the selective acknowledgement will tell him, okay, I'm waiting. I have 2 problems actually. It will telling him that this, you can see this kind of example here. It's telling him there is something called lower bound and upper bound on the left side and right side. Telling him, I'm waiting for two SAC blocks or selective acknowledge blocks, okay, as mentioned here in the description. The first one, 300 to 399, and also I need this one 669. I didn't receive both of those, so please retransmit both of them. Um, this is how it looks like. For example, I will show you quickly from one of the Wireshark how it looks like from Wireshark whenever the is going to have a retransmission. Okay. So I'll show you how it will looks like in the Wireshark itself, but this is how it will looks like. It will have the left side and right side and how many blocks it would like to retransmit. So what will happen directly, the sender is supposed to send the missing packets at one go, or different like directly afterwards. So this is like can again repair both of them. So the advantage that with the SAC or a selective acknowledgement, the sender doesn't rely on duplicate acknowledgement to infer gaps and eliminating the need. This is eliminating the need for repeated acknowledgement for each hole. Yeah. And in general, there is usually it can repair up to 3 or 4 per SAC. Okay, so each SAC can have asking for a recovery for 3 or 4 segments, up to 4 segments within a single round trip time. And this is again it contrasts with the duplicate acknowledgement. We're required to send multiple duplicate acknowledgement. Let me quickly show you the Wireshark example. Then we'll be ending by the last part, which is related to the relation with the PDCP as well. I already discovered some of them in between, but let's go in the last slide to see. But first, let's go through the Wireshark example. So in this example, let's first quickly recap this kind of capability, how to check this select acknowledgement. So this is the handshake in the very beginning here. You can see if I click here, in the send message, bottom down in the TCP transmission protocol, you will find the TCP options down here. If you go to the options, you will find under the options, if you click it here, you will find something called, again here, the SAC permit. It means I'm supporting SAC. Select to acknowledge. Same for the application. It will also send their capability. If you go down to the TCP header, also saying that I'm supporting as well the select acknowledgement, because as I mentioned, it's a bidirectional communication. Okay. So now let's jump into the packet, which is showing that first of all, there is a gap or there is packets being missed in between. So I will go for this packet number, which I know where is it exactly. So if you look into this part here, there was a packet transfer from the application to the client. Okay, as you can see here, and every time, like if you look quickly here, this is, for example, till this packet here, just multiple packets being transferred. Then in this one, telling him, I'm telling here the sequence number is this number, and the next one should be 10444518. So whenever the client is going to respond to an acknowledgement, should be this number, which is the next request number. So if you look forward here, the acknowledgement here replied with this packet, which is 10444518. If you click again in the previous one, you will find the next one is 105518. So the client is saying, I'm waiting for the next one to be this one. So you'll find the next one is 100518, and again so on. Then suddenly what happens? When this packet being sent, which is packet number 1013, okay, when it's being sent here, it was telling him, I'm waiting for packet number 104889. This will be sent, next one I'm going to send. So the client is expected that he should receive next this one, but see this one from the application to the server. It sent 10955618. You can see here, this is the message saying TCP previous segment is not captured. There is a packet is not captured. This is from the Wireshark because the expectation was to send 10488898. This means you have now a gap. I can't tell you exactly how many segments or packets. Like for example, simply you can do what? You can extract this one minus this one, then divided by the segment length. It will give you the number of segments being lost in between. But this is not our message now. Our message that once the client detect there is a missing packets, it will start sending called this kind of it's called TCP top ACK. But if you look down here, okay, you'll find in the right side even here, length equals 0, SLE, SRE. This is the left side, right side. Let's go down to the selected knowledge to see what we have. Here, I'm sending here. This is just asking to retransmit, by the way. So go down to sec, okay, TCP, okay, very good. Under the option, you have the TCP option. See selective acknowledgement 105618, tell 105, tell him I need the packet from here to tell here. I'm waiting for this kind of segment which is left edge this number and right edge this one. The 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 client will keep doing the retransmission until the, the application server send this packet, which is starting from 1048898. It will keep sending. Again, by the way, this is not something will stop the transmission. The sender still keeps sending, but again, the receiver will not being able to send it the layer to the application layer until it have the packets in sequence. So it will keep buffering the data until it have the complete sequence and until recover the data here. So if you look into here, I just jumped to the message directly. It kept sending that I need this data. If you look into, for example, down here, if you keep going down, it will tell him 1050538. Then if I move down, it will keep the left edge would be fixed. Then it will keep highlighting what kind of segments being lost in each and every segment, as you can see here. Then it will not stop until it receives the retransmission, which is here, as you can see. The application server now is transmitting the packet starting from 1048898, which is being missed at the very beginning. And this is how it looks like. Now let's go back to the slides to see what we have next. So in this slide, I'm going to summarize what is the expected impact and in general, why that does the PDCP receiver in general in the PDCP ensure there's in-sequence derivatives over there. Okay, let's first recall one of the message which is explained in the very the flow which is explained in the session 1 and 2 as well. If you remember, we have at the this is a transmitter receiver. This is the complete end-to-end flow. I'm assuming that TCP is over here, but as you know, there is many things in between, as I showed before in the end-to-end call flow. But just this is for to make it more simple. So if you remember, we have one parameter called reordering at the PDCP receiver. This reordering timer is just the PDCP if received out of sequence packet from the sender, PDCP sender, it will keeping reordering these packets, waiting for the packets in order to make sure that packets is being sent in sequence to TCP. Even when highlighted, the TCP have the capability, okay, the TCP has the capability of reordering the packets and it will reorder the packets before sending to the upper layer. But why still the PDCP take care of the in-sequence delivery? Because if you see the duplicate ACK and selective acknowledgement, okay, this means that if you send a lot of packets from the PDCP layer to the TCP out of sequence, this will increase massively the number of retransmission. That's why you need to ensure as much as you can from the TCP side receiver that whatever packets you need to transfer in the TCP is try to make it in sequence to avoid this kind of retransmission and wasting resources and delay, increasing the delay. So that's why the PDCP receiver ensures sequence delivery to first of all avoid increasing the latency because out of order packets that it must be reassembled by the TCP, right? And this introducing delays while waiting for the missing packet or rearranging the received one. And again, this is can, for example, affect the low latency application, for example, gaming, VoIP, or whatever. Okay, and also it can reduce the throughput. Imagine that you have massive number of retransmission. But part of the control flow control of the TCP, which I didn't go through in details of it, when there is a lot of retransmission happening, so what will happen? The receiver will understand, in general, retransmission is an indication for a congestion network. So the receiver or the sender will understand, especially the receiver, if there is a lot of retransmission, that there is a network congestion. So it will reduce the window size, will do this kind of window size in order to ask the sender to reduce the rate of sending the throughput. So this can the data. So this can again impact and degrade the performance, especially in the heavy traffic scenarios whenever you do heavy download, for example, FTP or whatever. Also, this can have a variation in the packet arrival. So this variation can impact the jitter. As you know, jitter is usually impacting the variation in the latency. Also, can have some impact in the quality of service. This is like if there is any quality of service, like you would like to match or match a specific quality of service, and also the processing overhead for the CV in general is being impacted. So this is the overall like impact and why we need the reordering. So in general, like this is can be different from different perspective of different devices or different algorithms, can be different from a standalone to non-standalone. I have highlighted in the previous session what is the causes which can cause out of sequence delivery in general. So this is like making this value very high. It can keep the data holding the data here without transferring to TCP. So this can increase the delay a lot, can increase the latency, and also can trigger indirectly in case if it's very, very high, it can trigger even the sender from the TCP based on the RTO timer to make the retransmission. So that's why increasing this one very high is not that good. Very low also is not good, because if it's very low, at the very end will increase the retransmission on the TCP side. This can impact the heavy traffic side. And one point to remember, the PDCP itself, PDCP layer, whenever it receives packets from the TCP, it doesn't know. It doesn't know. For example, the TCP is like for one device. Let's assume I'm the device. I'm doing the download, okay? And in the same time, I'm doing HTTP. And I did multiple activities, each one of those having different TCP stream. TCP stream means that different application server. The BTCP itself, it doesn't know. Like if it's receiving the data, just receiving data as packet. So giving a sequence number and like keep increasing the sequence number. It doesn't know that this is a packet for different, for example, data stream. So for example, assume I'm doing like Google, browsing Google, and doing YouTube, and also I'm downloading the file at the same time. I assume there was a sequence delivery in the, let's say in the file, the fast file transfer, which is FTP. So the BTCP, this means the BTCP will hold the packet at the receiver, okay, until you receive the correct manner of pattern of packets. So in this case, it can, for example, increase the delay for other two activities, which is HTTP, for example. So that's why, for example, if you get this timer very high, it can again increase the latency a lot, and if it's very low, again, it can increase the retransmission, so it can back the through. So you try to give an optimum value, and considering standalone and standalone, also different application or server, and this is for sure it will be different from one network to another. I know again the video is very like say intensive and extended like more than 1 hour. I tried to cover as much as possible, and the main idea here that I'm trying to correlate or like relate this to the radio RAM protocols, because at the end it's very important for radio engineers to understand what's happening in double layers, because at the very end, if you take any action and you don't understand what's happening in the TCP or double layers, this can impact negatively your end-to-end performance, even if sometimes you can see improvement from the RAM, but this is not, might be not the right way if you don't have the visibility over the end-to-end KPIs. That's why it's very important to understand all of that. And that's it for the third session. Stay tuned for the next session, which will be about the MAG part. I'll try to cover like also within the same perspective what is kind of relation, especially for the retransmission part, and how the retransmission handling and round trip time can be estimated from the 5G and so on. So just stay tuned for the last session. It can be one or two, depend on the gain session, because I don't want to go for more than 1 hour. So stay tuned, and thank you very much, and see you in the next video. And please again, uh, make sure to share and spread the word. If you like the content, please like it and share it with your friends. Thank you very much, and see you next video.